Okay, so let's start. In the last class, we were looking at two algorithms for one-dimensional convex optimization. Right? These are essentially search methods where you start with some range over which you know the minimum exists, and you iteratively try to reduce this search space by some factor. In the golden section search, we didn't even need convexity. All we required was that the function be unimodal, and you don't even need differentiability. As long as you can evaluate f at every point, that is sufficient. And we saw that by choosing parameters appropriately, it's enough to just evaluate f of x once per iteration. Right? And then we saw another technique called the bisection method, which converges faster, but it requires that the function be differentiable. As long as the function is differentiable, it need not be convex, but as long as it is differentiable and there exists a unique minimum, this is guaranteed to do better than the golden section search. So in this class, we'll see another technique wherein we sort of make stronger assumptions. So initially we didn't require differentiability. Then we came up with an algorithm which requires the function to be differentiable. And then now we'll see another algorithm which assumes that the function is twice differentiable and is convex. And the algorithm that we'll see is one of the main algorithms that is used for general convex optimization problems. In fact, it's so general that it applies not just to one-dimensional convex optimization, but also to higher dimensional convex optimization problems. Okay, but before we move to that, any questions from the previous class? No questions? Okay, so let's move on. So this is what is called Newton's method, right? And the fundamental idea behind Newton's method is you approximate the function by a function that you know, that you can minimize very easily. And what is that function that we're interested in? So suppose you're given an arbitrary function f from R to R, which is convex and twice differentiable. Okay. Now we'll try to approximate this function by a quadratic function. Right. Now, if you're given a quadratic function, let's say g of x equal to a naught plus a1 into x minus x1 plus a2 times x minus x1 the whole square. What is the, so under what conditions will this have a unique minimum? Is g of x always convex? Okay, so under what conditions is g of x convex? So a2 should be greater than 0. Strictly greater than 0? Okay, greater than or equal to 0. So is a linear function convex? Yes. How many say yes? How many say no? Okay, why do you think the linear function is not convex? Yeah? Correct. So it is, can you go back to the original sort of definition? Okay. Correct. Exactly. So it's always less than or equal to, the curve is doesn't necessarily have to lie strictly below the straight line joining 2 points. Uh, what we definitely don't want is that it's never above the line joining those 2 points. So the linear function is always convex. Right? So g of x, so any quadratic is convex if and only if a2 is greater than or equal to 0, because then the second derivative would be greater than or equal to 0. Right? Okay, so suppose you had to approximate f by a quadratic function. How would you go about doing this? What is a standard technique that you've seen in high school? Yeah? Discriminant. Okay, how? You're given an arbitrary function f. Yeah? Taylor series, right? So you look at the Taylor series expansion of f and you just stop at the quadratic term. You just eliminate the rest of the terms in the Taylor series expansion. Okay? So that's basically what Newton's algorithm tries to do. So suppose you have an initial estimate, let's call it xt. All right, so this is our, say, the current point. All right, the next point, so to find the next point, you look at this function gt of x, which is basically the first three terms in the Taylor series expansion of f of x, which is taken around xt. Right, so this would be f of xt plus x minus xt times the first derivative of f evaluated at xt plus x minus xt the whole square by 2 times the second derivative of f evaluated at xt. So for a general f which is continuously differentiable and all the higher order derivatives exist, there would be more terms in the Taylor series expansion. But we're going to just stop after this particular term. It's an approximation of f, right? But this is an approximation that we know how to minimize exactly. Correct? So in this case, what would be, suppose I had to minimize this function gt of x, what would be the point of minimum? So firstly, are we guaranteed that gt of x is convex? Yeah, so the question is, so we know that f is convex, that is given to us, and we're looking at an approximation, right? So the question is this approximation also convex? Yeah, and why is it convex? Correct. So for gt of x to be convex, we just saw that the coefficient of x minus x1, the whole square, should be greater than or equal to 0, which must mean that f double dash of xt should be greater than or equal to 0. But we know that f is convex, so the second derivative must be greater than or equal to 0. So the answer is yes, since xt is definitely going to be greater than or equal to 0. Okay, so now that we have this, let's try to minimize this function. So what would be the point of minimum? So we want to find minimum overall x in R of gt of x. Okay, so it's unconstrained minimization of this function gt. How would you do this? Sure, but how would you get this? Just take the derivative, set it equal to 0, right? Let's do that. So what is the first derivative equal to? It's x is f prime of xt plus, yeah, plus, note that this is a function of x, right? So in this xt is really a constant for us. And when I'm saying the derivative, it's the derivative on the left hand side, it's the derivative taken with respect to x. So this plus x minus xt times f double dash of xt, you want to set this equal to 0. So xt would simply be x, the minimizing x would simply be xt minus f dash of xt divided by f double dash of xt. Correct? So we can minimize this exactly, and this is what we'll take xt plus 1 to be equal to. Right? So the Newton's algorithm is essentially the following. You are given f, and you start with some x0, and you keep repeating the following: I equal to 1, 2, 3, and so on. You do the following. So you set xi to be equal to xi minus 1 minus the derivative of f evaluated at xi minus 1 divided by the second derivative of f at xi minus 1. I'm sorry? X naught is some arbitrary initial choice. Okay? So one thing to be kept in mind is that for this to work, we want the second derivative of f to be strictly greater than 0. Otherwise, this won't work, right? Because if the second derivative were not greater than or equal to 0, then this would not be a convex function, it would be a concave function. Correct? And this would not really be the minimum of that particular. It will not really be a minimum. Correct? Okay, yeah.
So when we differentiated g,
correct,
then are we ignoring the f triple dash?
Yeah, so we're basically just approximating f using just the first 3 terms of the Taylor series expansion. Okay, that's the basic principle behind Newton's method. All right, so we're approximating one convex function by another convex function, which is easy to minimize. Okay, so sometimes in optimization theory, such a function, such an approximation function is called a surrogate function. So instead of minimizing f, you try to minimize g, and you do that iteratively. All right, any questions? The question is, at what point do we terminate this? Right. So earlier, in the previous two algorithms, we knew when to terminate, because we were always, or at every step, we were keeping track of the interval ai bi, right? And the difference between bi and ai would tell you the error or how close you are to the minimum, to the true minimum. That's a rough estimate. In this case, how do you do this? How do you do it? You simply look at ai and ai minus 1. Okay. So one way of terminating is you look at not ai, I'm sorry. So xi minus, if xi minus 1, if this is less than or equal to some epsilon, then you terminate. So at this point, we leave this as a heuristic algorithm, but we'll revisit it once we start analyzing higher dimensional convex functions and higher dimensional convex optimization. Right? We'll see why it works and what is the rate of convergence of this particular technique. All right. So of course, when you look at this algorithm, you see that in some sense, the rate of convergence would also depend on this second derivative. If the second derivative is reasonably well behaved, then this converges reasonably fast. But this algorithm is also sort of another way of looking at another algorithm which you may or may not have seen earlier, called gradient descent. So suppose that you take a function f. All right, let's just take Newton's method itself. Right, I have this function f. I start with an arbitrary initial point. Let's call this x0. Now from this x0, I have, of course, so this is my x0 and I want to evaluate x1, correct? So my x1 is going to be x0 minus the derivative of f evaluated at x0 divided by the second derivative. Now I know that the second derivative is always greater than or equal to 0, correct? So in which side will x1 lie? All right, in this case, what can you say about the derivative of f at x0? Is it going to be positive or is it going to be negative? It's going to be negative. So I have x0 minus a negative quantity, whatever that is, right? So where will x1 lie? To the right side, correct? So it's going to, in the first step, it's going to move in this particular direction on the right hand side. So maybe with that I get to some other point x1. All right, now once again I do the same thing, right? Where would x2 lie? It would lie somewhere on the right hand side. So maybe I move to x2 and once again I do the same. Maybe this is where x3 lies, right? Now what is the derivative at this point going to be? Positive, right? So if the derivative is positive, so x4 is going to lie on the left hand side or right hand side? Left hand side or right hand side? It's going to lie on the left hand side because x4 is going to be x3 minus the derivative of f at x3 divided by the second derivative at x3. So this quantity is always greater than or equal to 0. This quantity is also positive now. So it's going to be x3 minus some particular quantity. Right? So I'm going to make a jump here and so on. Right? So at every step, this algorithm is moving in the direction of the point of minimum. Okay. Now, another algorithm used for minimizing not just convex functions, even potentially non-convex functions, is called gradient descent. And it works as follows. So you take xt plus 1 equal to xt minus some delta t times the derivative of f at xt. Okay, where delta t is some step size which is always chosen to be non-negative, and the derivative is of course the same. Again, the main intuition behind this algorithm is you always move in the direction of the minimum, right? In higher dimensions, we'll see that this is the direction where this is going to be the negative of the direction where the slope is maximum, right? So this is what is called gradient descent. And this potentially can be used for non-convex functions as well. All right. So maybe let's quickly see an example to see what happens. So I'll deliberately choose a non-convex function just to illustrate what Newton's algorithm could look like. So let us take f of x equal to negative e to the minus x square by 2. Okay. Is this function convex, concave? Concave. So what does e to the minus x square by 2 look like? So it looks like the Gaussian curve. It looks like a bell-shaped curve. E to the minus x square by minus e to the minus x square by 2 is the negative, right? So it's going to look something like this, right? But is this really convex? I mean, even visually. So let me just plot. Okay, let's see. Let's take x to be minus 3 to 3. Okay, maybe this is sufficient for us, right? So is this convex? For x greater than 0, you say that it is convex. Is it? For x greater than 0, it's convex. Are you sure? I mean, just visually. Let's see what happens. You take a point over here, and let's take the point x equal to 1. Where will the straight line joining these 2 points lie? Will it lie above the curve or below the curve? Above the curve. Let me take a point x equal to 1 and another point, say x equal to 3. Will it lie above the curve or below the curve, the straight line? It's going to lie below the curve, right? So it's in fact neither convex nor concave, but there is a certain region, as you pointed out, a certain region where it is convex, and there's another region where it is concave. Okay, you have to be a little careful as to at what point it is convex and what point it is concave. Okay, so suppose I'm trying to minimize this function in a small neighborhood around 0. I know that the minimum is at 0, but let's suppose I'm trying to use Newton's method to minimize this particular function. Okay. So let's try to evaluate the first derivative and the second derivative. That's what we require, correct? So what is the first derivative of x going to be equal to? It's going to be x e to the power minus x square by 2. What about the second derivative? Yep, e power minus x square by 2 minus x square e to the power minus x square by 2. Okay, so I have this. So let's see what would Taylor's algorithm look like? So or maybe even before that, what does gt of x look like? This is going to be minus e to the minus xt square by 2 plus x minus xt times x e to the minus xt square by 2 plus x minus xt the whole square by 2 times e to the minus xt square by 2 minus x square e to the minus xt square by 2. Correct? So maybe let me take a point and see what this looks like. I have f, I have x. Let me take x t to be equal to say 0.5. Okay. So what is f of xt? We call this f0. This is minus x. So this is my f of xt. The first derivative of f evaluated xt would be xt times minus xt square by 2. Second derivative, this is e to the minus xt square by 2 square by 2 minus xt square times minus xt square by 2. Right, so this is what we have. And what would gt look like? It's f0 plus x minus xt times f1 plus x minus xt the whole square by 2 times f2. Correct? So let me plot x and f, and also gt. So this is what it would look like. So our function, the blue line, essentially the blue curve corresponds to the true function f that we're trying to minimize. But we're looking at only at the first two terms in the Taylor series expansion of f evaluated at 0.5. Correct? So this is our xt, and instead of minimizing the blue curve, you would try to minimize this red curve. So your xt plus 1 would be the minimum of this red curve, which would be whatever, somewhere around here, slightly negative. And this would keep proceeding, right? You iteratively, so your new point would be somewhere around here, maybe around 0.25 or 0.75 or so, and yeah, somewhere closer to say 0.25 or 0.3. And then you look at the Taylor series expansion at that particular point, and so on and so on. I'm sorry? Right?
Yes, repeated like you said. It is like we are minimizing the quadratic equation. Right?
Yes.
Sorry.
The quadratic function.
Quadratic function.
Correct.
So we are getting the minimum of it, and
Correct.
that would be here, like
That's my new xt.
equal to, like, near to the.
That will be closer to the point of the minimum. Yes.
Again, is it Taylor series or what?
Now again, at that point, you find the Taylor series expansion of f around that new point. Correct. So that will give you a new quadratic
Like
function.
instead of x of t, or substituting that one.
Correct. Exactly. So you have an xt plus 1, right? And you find the quadratic at that particular point. So maybe just to illustrate, so this is your, perhaps this is what my function looks like. You start with some particular point. This is my xt. I look at the quadratic around that particular point, right? So maybe this is the quadratic, and this would be the point of minimum. Now you look at the Taylor series expansion of f at this particular point, right? So this would give me a new quadratic function, right, which maybe looks like this, right? So you find the minimum of that particular point, and so on and so forth, right? Does that make sense? Okay.
Do we get the exact minimum of that function, like, or else it would be like this?
So all you can say is that eventually this is going to converge to the minimum. Yes, if the function is convex. That's why we'll analyze this algorithm in more detail in a later part of the course, where we'll deal with this algorithm in full generality. Right? Again, unlike the previous algorithm, which essentially were search algorithms, you take the real line and you partition it into subsets where you search over. This particular algorithm, it in general can hold, is valid even for higher dimensional functions, right? And we'll see how fast the algorithm, later on we'll also see how fast the algorithm converges to the minimum point. So first, that this function indeed, this algorithm converges to the minimum, and secondly, how fast it converges to the minimum. Any questions?
So the Newton method also works for non-convex function.
The Newton method in general won't work for non-convex functions. Can you say why?
Sir, I was doubtful because the double derivative might be less than
Negative,
0.
correct. In which case, what would be the minimum of that quadratic? Where would the minimum lie?
The maximum.
Okay.
The derivative is less than 0. Then
Okay.
it will become a downward facing quadratic.
Correct. But then why is that? Why should that be useful? So it will turn out that if you try to do that, the algorithm might simply oscillate without converging to any point at all. Okay, you can sort of construct toy examples where if you try to do that, you just keep oscillating, right? But instead, if you know that the function is not convex, then a better algorithm to use is this gradient descent, which is always guaranteed to move in the direction of the minimum. The problem with, say, just directly using this particular approach is that suppose that the second derivative is negative, correct? Then you said, why not just find the point of maximum, correct? But in what direction would that maximum lie? It would actually lie in the opposite direction to the minimum, if you think about it a little carefully, right? In fact, even in this example over here, right? So this was the point that we started with, correct? And then it moved towards the minimum, correct? Now let me take another point. Right? Let's take xt to be equal to say 2. Okay, and now I'll evaluate all of these quantities once again: the function, the first derivative, the second derivative, as well as the function gt. And now let me plot this particular function gt x comma f right. So we started out with this particular point, correct? And if you look at, so this gives you the quadratic approximation of the function around 0.5. But where does the maximum of this red curve lie? It lies somewhere to the right, correct? Right of 0.5. Sorry, I started with I think 2. So the maximum would actually lie somewhere slightly to the right of 2. Okay. So you're not moving in the direction of the gradient. In fact, this particular, so this new xt, so xt minus the derivative divided by second derivative, this would actually be the point of maximum of that curve, of the red curve. But since the second derivative is negative, you will actually be moving in the opposite direction to that of the minimum. So instead of moving towards it, you're moving away from it. So there's a tendency to sort of move towards the minimum and then away from the minimum, and so on and so forth. Right? So Newton's method is guaranteed to work only if the function is convex. Right? Any other questions? Okay, so now we've seen one-dimensional convex optimization in some detail, right? But that's not all there is, right? So higher dimensional convex optimization is something entirely, it requires entirely new tools, but we will try to use these intuitions that we've gained from one-dimensional convex optimization even in higher dimensions. So if you recall, we want to solve like really complicated optimization problems, not just some functions over Rn, but as we saw in a previous class, also functions like log of the determinant of some matrix, where the maximization is taken over some subset of matrices, maybe positive semi-definite matrices. All right. And in order to solve optimization problems of that kind, we need to develop mathematical tools wherein we can analyze all of these under a single common framework. All right. So, but before we get into that, we'll want to revise our multivariable calculus and also develop it in a slightly more formal way, slightly more formal than probably what you've seen before. So we'll go through some of these definitions a bit rigorously. Again, these are topics that require entire courses. So we'll be very brief, but we still want to get our foundations right. Right? So we'll start with some basic real analysis, where many of these things are what you've seen before, but in a slightly more formal way. Right? So we'll start with something simple. So given a set of real numbers, what is an upper bound? What is a lower bound? What do we mean by the supremum, the infimum, the maximum, and the minimum? Right? So suppose I give you some subset of real numbers, right? So what do you mean by an upper bound for S? X is yeah.
For all y belongs to S, y less than.
Correct. So y is less than or equal to x for all y that lies in S. Right. Similarly, lower bound. But now given a set S, what do we mean by the supremum of S? So we say that it's a supremum if it is the smallest upper bound in some sense. All right. So firstly, X should be an upper bound for S. Right, and it's the smallest upper bound, which means that if we have any other upper bound, is any other upper bound, then y would be greater than or equal to x.
X belongs to the set itself.
We'll just see it for a moment. We'll see that. Okay. So this is also called, the supremum is also called the least upper bound. All right. So let's look at some examples. All right. Let's take the set, the closed interval from 1 to 2. What is the supremum equal to? So any number that is greater than or equal to 2 is a valid upper bound for this particular set. Correct. And what is the least upper bound? 2. Right, that's straightforward. So the supremum is equal to 2. Okay, now let's take the open interval from 1 to 2. Again, any number greater than or equal to 2 is an upper bound for this particular set. If I take any number less than 2, is it an upper bound? It is not, correct? No matter how much lower below 2 I go, I can always find a number greater than or equal to that in this particular set, strictly greater than that in this particular set. So what would be the supremum of this particular set? Again, 2. But unlike the previous example, 2 does not lie in this particular set. Alright. So just as we define the supremum, we can also define the infimum. So the infimum is, again, x should be a lower bound for S, and if we have any other lower bound, then that should be strictly less than or equal to this particular lower. So it's the greatest lower bound. Right. So just as we saw in these two cases, that the supremum may or may not lie in this particular set. If the supremum lies in the set, then it has a special name. It's called a maximum. So if the supremum of S lies in S, we call it the maximum. So similarly, if the infimum S also lies in S, we call it the minimum. Okay. So let's go back to this particular example. In both these cases, the supremum exists and is equal to 2, correct? But what about the maximum? What is the maximum of this first set? Maximum of this set 1 comma 2 is equal to 2. But what about the second term? Yes. So even if I take open interval, this does not exist. Right? So for a given set of real numbers, the maximum may or may not exist, but the supremum always exists. And in particular, suppose that the set is unbounded on the right. Right? So there's no maximum value. So in other words, if S is not bounded from above, we'll define the supremum of S to be equal to infinity. Right, so that's going to be our definition of supremum. Similarly, if it's not bounded from below, then we'll say that the infimum of S equals minus infinity. Right? In both these cases, the maximum and minimum do not exist. you take any non-empty subset of the reals, it will always have a well-defined supremum and a well-defined infimum, but the maximum and minimum may not exist. And again, this is important because suppose we are trying to optimize a function subject to some set of constraints. The function may have a supremum, it may have an infimum, but it's possible that the maximum and minimum do not exist. So in other words, it's not possible to achieve the maximum. As an example, let's just suppose that we're trying to maximize. So consider trying to maximize say x square subject to x lying in the open interval from 0 to 1. Okay. So whatever constraints I have correspond to some open interval, let's say. Now in this case, what is the optimizer? What should be the optimizer? So instead, if I had supremum of x square, x lies in 0, 1, what is this equal to? It's equal to 1, right? So it's equal to 1. But the maximum of x square for x in 0 to 1 does not exist. So even though this you have a supremum, it cannot be achieved. That's why we need to be careful. So if I try to come up with some kind of an iterative algorithm, that would still be fine because it would be somewhere close to 1, it would never get to 1. Okay. That is why just because some optimization problem is feasible, that is the constraints can be satisfied, does not mean that it has a well-defined optimizer. The maximum or minimum may not exist. But if you slightly relax the problem of just asking the supremum or the infimum, then that may exist. All right, any questions? Okay. So it's for a set, any arbitrary set.
Then, instead of writing the supremum of that set, you're writing it for x square, right?
Correct.
Like, then why are you writing it for x?
Because that's what we want, right? Ultimately, our goal is to solve some kind of an optimization problem. Correct. So if another way of thinking about this is I'm looking at the range of the function. Correct. And I want the maximum or the minimum if that exists, or at least the supremum or the infimum. If I'm trying to solve a maximization problem, it's the supremum. It's a minimization problem, then it's the infimum. So they're both equivalent. All right. So again, we will be looking at infinite sets, but there are different kinds of infinities, right? Have you seen what a countable set is? How many of you have not heard of the term countable set? Okay, it's okay to say if you've not seen it before. Okay, so how do you define a countable set? Yeah. Okay, so a set S is countable if not necessarily a bijection, if there's a one-to-one map with the set of natural numbers, S to the set of all natural numbers. So obviously, by definition, the set of natural numbers is countable. What about the set of integers? It's countable. What about the set of rational numbers? How many say it is countable? How many say it is not countable? Okay, so why do you think it is not countable? Because it's not clear that we have a one-to-one map, right? So the first point that you'll agree with is that the set of rational numbers is essentially the same as set of all pairs of integers, right? Because you can just look at it, numerator divided by denominator, right? Okay, now the ones who said that it is countable, how do you show that this is countable? Yeah. Okay, but I don't know if this is countable or not, right? No, I agree that these two are equivalent, but why is either of them countable? You need to come up with a one-to-one map. You can? Okay.
Like you can start with a spider, right? Like you're comparing with integers. So I start my 0, 0 with 0.
Okay.
Like I will start with 1, -1, 2, -2. And so I will map the points along the way. Like a spiral starting from 1.
What do you mean? What spiral?
You're writing the.
An easier way is exactly as you said. You just map. You know that Z is countable. So there exists a one-to-one map from the set of integers to the set of natural numbers. So if Z is countable, even 2Z is countable, and 2Z plus 1 is countable. So you map all the terms of the numerator to even integers. There exists a mapping from the numerator to the set of all even integers. And there's also a one-to-one map from the denominator to the odd integers. So there is a one-to-one. Okay. So in fact, if you look at q to the k, so set of all k tuples of rational numbers, this is also countable. So if it is not countable, it's said to be uncountable. What is the best example? Yeah. So set of real numbers, set of complex numbers, any continuous set. Okay, so fine. Again, we'll just quickly go through many of these definitions just to make sure that we're all on the same page. So suppose we are given an arbitrary function f from some set A, some other set B. Then we say that the set A is the domain and B is called the codomain. Right? An important thing to note is that when I say that a function is defined on some domain A, it means that for every element in A, there is some particular value in B that f maps to. Okay, but the reverse is not true. Not every point in B must necessarily correspond to some point in A. Right? So the set of all f of x for x in A, this is called the range. Right, so essentially I have some set A, which is the domain, and this is set the codomain. All of this could potentially get mapped to some subset of B. Right, so this would be the range. And similarly, I can also ask for the image of some subset of A. So image of S under F. So if I look at some subset S, maybe all of this gets mapped to some other subset, and this is called the image. Okay. So again, if we think about it in the context of our convex optimization problem, the function A could be the function f could be defined over some larger set, for example, the set of all reals. But then we're really interested in maximizing this or minimizing this function over some subset, the set which satisfies the constraints. So maximizing f is essentially the same as looking at the maximum of the image, the maximum of the image of the set of constraints under the function f. Okay. And similarly, if I'm given any set S prime on the right hand side, then the inverse, or even before that, for every, let's say, y in B, f inverse y is essentially the set of all points that map to y. There could be multiple points that map to this particular y, or there could be no points that map to y. So it is a set of all x in A such that f of x equals y. Right? So this is what I call the inverse image. And this set, this is actually a set. It could potentially contain no points. It could contain exactly one point, or it could contain multiple points. For example, if I take a quadratic, like f of x equal to x square, then f inverse of 0 is 0. There's only one point. F inverse of 1, there are 2 points, plus 1 and minus 1. And f inverse of minus 1 is empty. So this, it's not necessarily, so f inverse of y is not necessarily a function. Okay, so now that we have this, we'll be interested in subsets, not just over the reals, but also slightly more complicated spaces. For example, the set of all matrices, or the set of all positive definite matrices, so the set of all positive semi-definite matrices. And more often than not, we're always interested in different metrics. How close are we to the minimum, right? Or even the functions that we're trying to minimize or maximize may be some kind of a metric. It could be some kind of a distance. So what is a metric? So suppose we are given some space, let's call it A. More often than not, we'll be looking at vector spaces, and we'll be trying to define metrics over these vector spaces. So a metric on A is basically going to be a function, right? So if you think of a distance metric, correct, what kind of a function is it? It takes 2 points, then spits out a number, right? So a metric is basically a function, and outputs some real number, but it's not any arbitrary function. It has to satisfy some properties, right? Similarly to what, let's say, the Euclidean distance would satisfy. So what are the most basic properties that the Euclidean distance must satisfy? Yep, so we want the distance to be greater than or equal to 0 for all points. But when can it be equal to 0? So it's equal to 0 only if x equal to y, right? So if I take any two distinct points, the distance between those 2 points is strictly positive. Okay. And if I take a point and find the distance from that point to itself, that should be equal to 0. That's one basic property. All right. What else? So it should be symmetric, because the distance from x to y should be the same as the distance from y to x. Okay, and what else? Which one?
For the distance.
Okay. That's right. Yep, so it should also satisfy triangle inequality. It says that if I take 3 points x, y, and z, then the distance from x to z should be less than or equal to the distance from x to y plus the distance from y to z. So if I take any 3 points, then these correspond to a triangle, and the shortest distance from one point to another should always be greater than or equal to the distance of the path taken via some other. Okay, so any function that satisfies these 4 properties is called a metric. Right? And it's easy to verify that the standard Euclidean distance. So you take any 2 points, so if I take any 2 vectors x and y, this forms a metric. But what if I take d square xy, which is just the squared Euclidean distance? Is this also a metric? How many of you say this is also a metric? How many of you say this is not a metric? Okay, so firstly, it satisfies the first three properties. That should be clear. It is symmetric. It's always non-negative, and it's equal to 0 if and only if x equal to y. Right? But does it satisfy triangle inequality? That's the whole question. Okay. So if yes, we need a proof. If not, we need a counterexample. Can you come up with a simple example, even in, let's say, 2 dimensions, where this is not satisfied? Okay. Okay. So let's take 0, 0 and some other point. Okay, maybe you want to take, yeah, you can explain your intuition first, and then we can maybe come up with the example. Okay.
The distance is like 1 and 6.
Okay.
7 square is not less than.
Okay, so you're taking just an example over R. Let's just take 0 and 7 and just the point 6, right? So what is the distance from this point to this point? It is 49. So let me call this x1, this is my x2, and this is my x3. x1 minus x3 the whole square, this is equal to 49. x1 minus x2 the whole square, this is equal to 36. x2 minus x3 the whole square, this is equal to 1. Right? So x1 minus x2 the whole square plus x2 minus x3 the whole square is just 37, which is less than x1 minus x3 the whole square. So the squared Euclidean distance is in fact not a metric. So we have to be careful. So all the properties that we assume that a distance should satisfy, the squared distance doesn't satisfy that.
So is the metric necessarily required to satisfy all?
Yes. So if some function satisfies these properties, then we call it a metric. It's a definition. Only these 4 properties. It's fine if it satisfies some extra properties, but we don't need that. Okay. And another metric is what is called the LP metric. So you take any p greater than or strictly greater than 0, and you define dp of x y to be summation I equal to 1 to n xi minus yi whole to the power p whole raised to 1 by p. So if you take p equal to 2, then you get the standard Euclidean distance. If you take p equal to 1, it's called the L1 distance, and so on. Okay. I claim that this is also a metric. Again, the first 3 properties are straightforward. All that one needs to show is that the 4th property is also satisfied. We'll revisit the LP metric later on, but this LP metric also has some other nice properties as well. This is called the LP metric. this should have thanks for pointing that out. Okay. So just as we defined a metric, we can also define a norm. So a norm is, you can think of the Euclidean norm. So a norm is basically some function on the set and outputs a real number R and satisfies the following properties. So what properties should the length of a vector satisfy? So once again, we want f of x to be greater than or equal to 0 for all x in A. What else? When can it be equal to 0? If and only if x equal to 0. Right, so it means that there's a special 0 vector. So we'll define all of these typically only on a vector space. All right. What else? So suppose I scale the vector by a certain amount, alpha times x. So throughout I'll use this underline to denote a vector, right? And scalars will not have underlines. So what should this be equal to? Correct. So the absolute value of alpha times the norm of x belongs to A alpha in R. All right. Anything else? Yeah. Triangular inequality. Which is what? F of x plus y should be less than or equal to f of x plus f of y.
Sir, A is subset of
Which one?
A.
So A is going to be some vector space over the reals. The reals. So the underlying assumption is that A is a vector space over the set of reals. Right? So basically all your scalars come from R and the vectors can be any subset. So Rn is the common example, but it can also be some subset of matrices or so on. So this is the definition of a norm. So if I take a distance, so suppose I have a metric, can I construct a norm from this particular metric? Or in other words, can I go the other way around? Suppose I give you a norm, can I come up with a metric? Mhm.
The norm of the difference between two vectors.
Correct.
That becomes the corresponding distance.
Yes. So if I have a norm, So if f is a norm, then if I look at the norm of x minus y, then this becomes a metric. Okay. Okay. So maybe let's stop here. All right. Any questions?